Filtering. I hope to finish this lecture today. So filtering is one of the most basic operations in any of signal processing systems that you might encounter. And filtering is the process by which relative amplitudes of the frequency components in a signal are changed, or perhaps frequency components are suppressed. And you must have come across some terms like low pass filter, high pass filter, band pass filter. That is what you're talking about. And they are characteristics of a system. So as you saw in the preceding section, for continuous time LTI systems, the spectrum of the output is that of the input multiplied by the frequency response of the system. This is something I've already said. Y of omega is, this is what I've already written here. And therefore, an LTI system acts as a filter or as an input, as a filter on the input signal. And here, the word filter is used to denote a system that exhibits some frequency selection or some frequency selective behavior. So you select some frequencies, you pass some of them, you stop some of them, etc. Now we have two types of or we have two classifications of filtering. One of them is ideal. We are going to start with ideal, and then we are going to discuss non-ideal. So to start with, the ideal frequency selective filters is one that with exact, here the word is exactly. The word here to underline is exactness. So that exactly passes signals at one set of frequencies and completely rejects the rest. So when you say the exact, if we have set our frequency filter to cut frequencies at omega naught, where this is omega and this is my my system bandwidth. So if I put the input that is having a higher, so if my input is having bandwidth that is probably up that point, but the system band or cutoff frequency is up that point, the whole of this will be cut out. The whole of that frequency will be cut out. And that if this filter of mine is ideal, every frequency that is above omega naught will be cut out. If it was not ideal, if I just use a different color, then you might observe that my filter will behave something like this, that probably the amplitude starts decreasing. So it is not cutting exactly at the defined value. It is trying to estimate how close your cutoff frequency, how close is it to your intended value. So that is the difference. The ideal will be exact, the non-ideal will not be very exact. And therefore, we have said that that is the point. The band of frequencies passed by the filter is referred to as the pass band, when the other one that is rejected is called the stop band. And the most common types of ideal frequency filters, or the filters, we have low pass filter, we have high pass filter, we have band pass that we'll see next, and band stop. So to start with the band pass, it is very straightforward that it's the frequency response will be one when your frequency of your input is less than the cutoff frequency. We have defined some cutoff frequency here. So here I use the symbol omega naught, but we can actually use omega c to mean cutoff. So when the magnitude of your frequency signal is less than the cutoff frequency, then it is multiplied by 1, meaning that your y is, you just remember this formula, y is equals to h of omega then times x of omega. So if this frequency response is equals to 1, then your y of omega will pass all the frequency components for the period or for the region of the frequency band within our cutoff frequency. If it is not equals to 1, it is equals to 0, then it means that your y of omega will be multiplied with 0, and therefore it will become 0, and therefore there will be no output. And we are seeing that this is shown in figure 5.5a, and figure 5.5a is right here. Oh, okay. Yeah, so figure 5.5a is here. And just remember that when we say magnitude of omega, it means that we are running from the negative value to the positive value. So we are saying that the magnitude value lies between the minimum and the maximum cutoff frequency. So we are saying that omega lies within this region. And that is why we are saying that it is low pass, meaning it is from 0 to the highest cutoff frequency that you have been given. And of course, these other symbols indicate the high pass, the high pass, filter, such that only frequencies that are above a given cutoff frequency are allowed to pass. And then this exam diagram illustrates the band pass that only allows some frequency within a certain band to pass. And lastly, this one is a band stop filter that will stop any frequencies that are defined within the given range. So all the frequencies in this range are stopped. And of course, this diagram is reciprocal. The word is not reciprocal, but rather it meets both sides, both the positive side and the negative side. So you might be able to cut off some frequencies on the negative side or some frequencies on the positive side. But what we are normally concerned about is the positive side most of the time, because you rarely deal with negative frequencies. So this is just a mathematical expression. Our most important concern is for the positive frequencies. So leave the negative frequencies alone. So having said that, so we have said this is how we define the ideal low pass filter. And of course, the reverse would be for the high pass filter, that for the frequencies that are less than the cutoff frequency, they are going to be multiplied by 0, and therefore they are going to be cut out. And the others that are bigger than the cutoff frequency, they're going to be multiplied by 1, and they are going to be passed. That is why it's called a high pass filter. So just like I have said, the ideal band pass filter would pass some frequencies that are within a certain range of frequencies, whereas the band stop filter will cut off or will reject some frequencies within a given range of frequencies. The point that we must always highlight when discussing the filters is the following, that we have said, okay, so far we have said nothing about the phase response of the filters, but what we normally require for the system to do, even if it is a high pass, low pass, or whatever, we say that it must maintain a linear phase characteristic. Otherwise, it is going to be to introduce distortion to our system, and therefore we require this to be the characteristic of our phase response. where TD, as we have already made before, is a constant. The point that I also wanted to mention regarding the filters that you're discussing, just as I said, is we consider the ones that we have discussed above are non-causal because they are considering both the positive and the negative frequencies. And this is how we define non-causal system. Just put in some notes here that says that non-causal system, the output appears even before the input is applied. And that is when you are finding some characteristic even when time is less than zero. But for a causal system, you always say that the output only occurs after application. Now the keyword is after application of the input signal, and therefore the output only appears when t is bigger than zero. That is why I was giving you in the previous diagram here that we are saying that if you want your filter to be causal, everything that is on the left would be trashed. Everything here you don't consider it. Therefore, you ignore everything that is on the left of these diagrams, and therefore you say that your filters are causal, and therefore they are only characterized on the positive side. So the area I have shaded illustrates that if those regions are not considered, then the system or the filters will be considered to be causal. Then we discussed briefly about the non-frequency selective filters, and we are going to start with an example that has been made before in figure 5.6a, which is described here. This is figure 5.6a. So assume you have such a system. It consists of an input voltage, an input source, some resistor, some capacitor here, and you want to observe the voltage at the output, which is uh, at the terminals of your capacitor. So the question is, how would you characterize that system? The first step, and this problem is covered in problem 132, is to just write the differential equations that describe that equation. And you can actually note down that this is the expression that describes the input-output characteristic of the system that I have just described. So having said that, the second step would be to take the Fourier transform of this differential equation, and then it will give you equation 591, and the 591 describes the frequency response of that system. And with that frequency response of that system, it simply now tells you what will happen to a signal when it's applied at the input, or what will be the behavior of the voltage at the output after application of some source at the voltage. And before we even go there, we can just see how is it that we are able to get that you have from this equation, you can get the Fourier transform of this one to be y of omega, and the Fourier transform of this, just like we applied a number of properties that we went through earlier. You apply the differentiation property here, and that means you introduce j omega to the Fourier transform of y of t, because this is because of the derivative, and then your constant remains there, and then your frequency response of x of t remains to be x of omega, and therefore you can do some simple manipulation here, factor out y of omega, you get, and then you divide by both sides by x of omega. This becomes your h of omega, and its value is given by 1 over j, y 1 over 1 plus j omega rc. And we say that if we set your omega naught to be rc, then you can characterize your frequency response as 1 over 1 plus j omega over omega naught. Then that is what we have done here. And so from this point, we are able to identify the magnitude response of our frequency of our system, and our system is this one. And we're also going to get the phase response of our system as described by equation 592 and 93 as such. And now, what we have simply tried to do, and as you remember, we are discussing non-ideal filters, and therefore we actually figure out from this diagram that we can simply draw directly from the equation that we have obtained here. This one is the magnitude response or the magnitude spectrum of our system, and this is, down here is the phase spectrum of our system. So when you look at the magnitude spectrum of our system, then you can clearly see that this is a low pass filter. And as I have mentioned, the ideal filter would have some definite values at which point the frequencies of the input signal are cut out. But since this is now a non-ideal, you can see that there is a gradual decline in the gain applied to your frequency, to your input, and therefore, as frequencies go beyond the cutoff frequency, then you observe that those frequencies are selectively cut off or rejected. So I think that this simply describes the magnitude response, which is describing the gain K that we mentioned that characterizes the magnitude spectrum of our signal, or rather of our system. And you also observe that when you draw the phase spectrum of your signal, you actually see that this is nonlinear. And then being nonlinear tells you that it is non-ideal, and therefore it will introduce some distortion to your signal, even if particularly when you are going beyond your the cutoff frequencies. So that is what we observe about that non-ideal filter that we have just exposed. We are saying that you can also get other filters, low pass, high pass, bad pass, or bad stop, just by applying the similar principles, except that they may not, they are going to follow the same idea that we have met in regard to how they selectively select the frequencies of the input signal. Now, our last subject to discuss today is bandwidth. You're going to meet bandwidth quite frequently when you're dealing with systems. Therefore, you might need to characterize what is the bandwidth of the system or what is the bandwidth of the signal. And you kind of get to meet these terms quite frequently. You'll meet the absolute bandwidth, you'll meet band limited signal, you might meet a half power bandwidth, etc. So for the sake of understanding systems and signals, we just discuss each of these. And the first one that we start with is the absolute bandwidth. And we say that the absolute bandwidth of an ideal low pass filter equals its cutoff frequency. That is from the figure 5A, the 55A that we have seen, the absolute bandwidth of that signal would be equivalent to its cutoff frequency. And on the other hand, the absolute bandwidth of ideal bandpass filter would be equivalent to the omega 2 minus omega 1. And here I just redrew this is a bandpass, ideal bandpass filter. And therefore, we are saying that if you wanted to find the absolute bandwidth of a bandpass filter, you'd simply get omega 2 minus omega 1, and then you say that is your absolute bandwidth of your high pass filter. Now, of course, on the other hand, it's quite straightforward, what I have just mentioned here, that if you are dealing with a low pass filter centered at 0, and here was your omega c, then you simply say that omega c is omega c, which is now starting from 0. This is your absolute bandwidth, which will be equivalent to omega c. Of course, this is what we are calling WB. Here you're actually seeing something here that if you are to get, okay, I think we are done with the absolute bandwidth, and we have also discussed the that of ideal band pass. And a band pass filter is called narrow band if its bandwidth is far much less than its center frequency. So here is the idea. You have said that this is your absolute bandwidth, the one that is the omega 2 minus omega 1. But if you wanted to find the center frequency of this filter, which is omega naught, omega naught would simply be obtained by omega 2 plus omega 1 divided by 2. If you realize that omega naught is far much less, well, rather the other way, is far much bigger than your bandwidth or absolute bandwidth WB, then you characterize your system as narrowband. And you're saying that there is no bandwidth. We don't define bandwidth for a high pass or band pass or band stop filters. The other quick concept that I will discuss is that of 3 dB or half power bandwidth. And we see the following, that for a causal or practical filters, a common definition for system bandwidth is the 3 dB bandwidth, which is symbolized as W3 dB. In this case, a low pass filter, such as the one that we have met earlier, is defined as the positive frequency at which the amplitude drops to a value equal to the magnitude of your signal at 0, and you divide it by √2. This is illustrated in figure 5.7a. Before we even go there, we are going to do some reading. Note that h of 0 is the peak value of your frequency response of the low pass filter, and the 3 dB bandwidth is also known as half power bandwidth. That is something we have already said, because a voltage or current attenuation of 3 dB is equivalent to power attenuation by a factor of 2. So here very quickly we are saying that if you evaluate the system response or the magnitude of your system or of your frequency response, and you find that its magnitude at 0 frequency is equals to 10. Let's say that h or the frequency response of your signal at zero frequency is equals to 10. That is the one we are calling the peak value of your magnitude. If your signal, as you now move towards the increase in frequency, if it drops by root of 2, then the bandwidth from 0 to the point where it has reached that 10 or h naught over 2 value, that bandwidth here is the one that you describe as half power band, 3 dB bandwidth. And I think here when I was doing my notes, I made a mistake. It's supposed to be from here. It's supposed to be from 0 to omega naught. So that is practically what we define as the half power bandwidth or 3 dB bandwidth. And you're saying that this definition of 3 dB bandwidth is useful for systems with unimodal amplitude response, that is in the positive frequency range, and is widely accepted criterion for measuring a system's bandwidth. It may become ambiguous sometimes for systems having multiple peak amplitudes or amplitude responses. We are not going to, for now, dealing with that, but a very unique term that you'll find when you're dealing with the systems is that we are always going to be mentioning half power bandwidth or 3 dB bandwidth. Just observe that they mean the same, and it is measured from 0 point to the point where the peak value of your system magnitude response drops by root of 2. So we note that each of the preceding bandwidth definitions is defined along the positive frequency axis only, and always defines the positive value. One-sided bandwidth only. So that is what we are saying, that we are defining our 3 dB bandwidth as that range when your system peak value or magnitude of your peak system response drops by root of 3. Then what we have dealt so far with is system bandwidth. And we are saying in a similar manner, you might also describe signal bandwidth. And therefore, you might have absolute bandwidth of your signal or 3 dB bandwidth, etc. So we say now that the bandwidth of a signal can be defined as a range of positive frequencies in which most of the energy or power lies. And this definition is sometimes ambiguous, but it is subject to some conventions, which we'll see later. So we at this stage, we may not be able to define the absolute bandwidth of a signal. What we'll start with is the 3 dB bandwidth of a signal. And we say now that the bandwidth of a signal x of t can also be defined the same way we have defined the system bandwidth, such that the 3 dB bandwidth using the magnitude spectrum x of omega, the signal. When it drops by root of 2, then we say that it becomes 3 dB bandwidth. And another term that we are defining here is the band limited signal. That will come quite often. Sometimes we say that a signal is band limited, and we simply say that the signal's magnitude drops to 0 when we exceed a certain limit that we are defining for that signal or for that limit. So some point we normally say that this signal, for instance, that my signal will behave like it will have peaks, then drops, and it all becomes 0. So if the magnitude of my signal drops to 0 beyond this omega m, then we normally characterize this signal as band limited signal. And that marks the end of what we planned to cover.